So welcome everybody. How's everybody doing? I think that was me, maybe. I don't know. So my name is Andy Robbins. I work at an organization called Spectre Ops. The title of my talk is How Graphs Changed the Way That Hackers Attack. Full disclosure, you should probably know that I do not have any kind of like formal mathematics or computer science education, and two of my colleagues do, but more or less we kind of relied on existing graph technology and kind of hacked together a solution that made sense for us. So I'm here to learn as much from all of you being graph professionals as anybody else. So I'm really looking forward to like talking with some people after this talk, and maybe somebody have ideas or improvements or suggestions or something like that. So without further ado, let's get started. So here's the outline of what we're going to talk about. I'm going to acknowledge some very important prior work, and then we'll start speaking the same language as far as how attackers actually attack corporations, what that actually looks like under the hood, what that looked like before Bloodhound and what it looks like now. I'll talk about the problem that Bloodhound solved, or that graphs solve for us, namely attack graphs. I'll talk about Bloodhound itself, future work for the project, and then at the very end I've got acknowledgements for some people who have helped us out a lot, and then a conclusion for you as well. Has anybody heard of Bloodhound? A few people, awesome, cool, okay. So I hope by the end of this, I hope that there's some kind of value that we can present, even if that is from an outsider's perspective, people who don't work in the same industry that you all do, kind of how our perception was shaped by, you know, Michael Hunger and other people's writings and stuff like that, and some of the conclusions that we came to as outsiders to your field. So this is me. My job, I'm the adversary resilience lead at Spectre Ops. What that means in plain English is I help organizations figure out how attackers can move through their network and help them shut down those attack paths as effectively as possible and as cheaply as possible, which an attack graph uniquely enables. I've been a professional penetration tester and red teamer for the past 5 years. What that means is I get paid to break into organizations, steal their data, and then write up a report and leave. And previously I didn't have to help them fix that, now I do. So it's not quite as fun as it used to be. I've spoken at a bunch of conferences. These are known in our field, so the Black Hat Conference, DEF CON, ISSA International, ISC Squared, Echo Party down in Buenos Aires, and then Paranoia Conference in Oslo. Has anybody ever heard of any of those conferences? Oh, cool. Probably Black Hat is probably the most well-known one. And I also give training at Black Hat, so Black Hat USA, Black Hat Europe, and then this year we were invited for the first time to teach in Singapore at Black Hat Asia, and we teach red team tactics, we teach adversary tactics, or how adversaries actually break into networks, and we teach people how to do these tactics. And then we also offer private training. So that was about me, this is about us. So there are two very important colleagues of mine who helped with the Bloodhound project. Rohan Vazarkar created the interface. So the interface I'll talk about and I'll show you, it's built on top of Linkurious, which itself is obviously built on top of Sigma. We did that because we don't know D3, we don't know Sigma. We needed some kind of abstraction away from that to build the tool with. And Linkurious was a perfect solution for us. Will Schroeder is an offensive capability engineer at Spectre Ops. He's known for a lot of situational awareness tools, namely PowerView, which is part of the PowerSploit framework, which is a PowerShell exploitation framework for Windows and Active Directory. Will created the first data collector for the project, which is going to make sense as I go more further in depth in the talk, like what all these different things mean. So some important prior work that I would like to acknowledge. First and most importantly, this is a white paper from Microsoft called Heatray, using machine learning and combinatorial optimization to combat identity snowball attacks. This paper came out in 2008 by Alice Jung and John Donegan and Daniel Simon. And unfortunately, the project never saw the light of day. Microsoft just shut it down. They couldn't figure out how to make money off of it. Whatever happened. It wound up like the Ark of the Covenant in a crate in a basement somewhere, never to be seen or heard of again. Active Directory Control Paths, this is a French project from ANSI, which is obviously a part of the French government. This was an important work where we learned a little bit more about graph theory itself, how vertices and edges relate to one another, and how to actually conceive of a graph design in an effective way. And then this project here called Active Directory ACL Scanner by Robin Gramberg at Microsoft. This kind of helped us understand more in depth how ACLs work in Active Directory. So no talk about attack graphs, in my opinion, is complete without this quote. This is by John Lambert, who's a general manager of threat intelligence at Microsoft. And John said, "Defenders think in lists, attackers think in graphs. As long as this is true, attackers will win." This is the title of a blog post that John put out 2 years ago, actually shortly before we released the Bloodhound project. And basically the concept here is that as defenders, you have a list of assets, a list of users. You do a vulnerability scan, you get a list of vulnerabilities. But as everybody in this room knows very well, disconnected data is not nearly as valuable as connected data actually is. So what do those vulnerabilities actually mean? What systems are they on? Who uses those systems? What data is on those systems? A list-based mentality doesn't answer those questions, whereas obviously a graph can and does, which is what we've done. So let's start speaking the same language a little bit. How do hackers actually attack corporations? There's a news story almost every week. Experian, Target, you name it. They're like Fortune 50 companies get breached all the time. And a common phrase that you hear is, "This was a sophisticated attack and there was nothing that we could do to stop this." Which, in our world, what that actually translates to is we were too lazy to do anything that our auditor told us to do, but we hope that you're going to believe us when we say this was like some nation state level attacker or something like that. So I'm going to show you like how these attacks actually work so you can see how little sophistication is actually required. Now, any corporate attack basically will follow a 4-step methodology. You're going to have a recon phase, which I'll talk about in detail, initial access, post-exploitation, and exfiltration. So these are the 4 phrases. Keep these in mind as we go into detail on each one. So recon. Recon basically means I know that I want to hack a certain organization. Let's say it's like a bank or a government agency. Or actually, I know, let's make it a little more interesting. Let's say we want to hack Neo4j. And I want to get like the source code for the next version of Neo4j before it comes out. Or I want to be able to cut myself enterprise licenses for free or something like that. To do that, I need to have access to a certain system at Neo4j to do that. I don't know what that system is. I don't know where it is. It's probably in their LAN somewhere, and there are probably people who have access to this. So I need to figure out who those people are. Who works there? What do they do? How long have they worked there? What's their job history? What can I find out about the individuals who work there to put together some kind of convincing phishing attack later on? So on LinkedIn, I'm connected to Michael Hunger as a first-degree connection. On LinkedIn, which is a social engineer's best friend or a hacker's best friend, any second-degree connection, I can see their full name and I can see their full profile, their job history, education, all that kind of stuff, endorsements. So even though I only have this one connection with Michael at Neo4j, he's connected with like almost everybody at that company, so I can see all of their names. I can put that together and I can form an email list. I can find out what their email address schema is from like Whois data or their website or their ICANN registration or whatever, a contact us page. I can put together a full listing of email addresses that I can use for a phishing attack. But what if I want to get really, really specific? What if I want to phish one individual person? Let's pick on Max. So Max, I'm a second-degree connection, but I can still see everything in his profile. So I'm going to scroll down and I'll look at like, what information can I glean about Max? And I come down here to his education. So he went to Florida Institute of Technology. He got a BS in computer science. Good for you, Max. But what's interesting is he was in a fraternity here called Tau Kappa Epsilon. So I'll do a little research about that. Well, at Tau Kappa Epsilon, there's this guy, Christopher Niles, who is the Alumni Engagement Director. So taking all this information together, the whole point of this is I want to find out as much information I can about the org. We've been focusing on people, but I can also look at technologies. What are their public IP ranges? What systems do they use? Do they use Macs? Do they use Windows? Do they use Active Directory? I can find out all this information in my recon phase. A quick, really fun story about this. We were doing recon against an organization that was really, really well defended. We finally got access to the network, but we had no idea where to go from there. We had access to somebody's workstation, but we didn't know, like, how do I get to the database server? How do I get to the domain controllers? What does the lay of the land look like? So we go back to our recon phase, and we ask the guy who did it, like, hey, do you have any information about the network? He pulls up this network engineer's Google Plus profile, like some random Google Plus profile, and the guy has a picture of his face, and in the background, on a whiteboard, he has the entire network diagram planned out for their entire organization. And he's like, there you go, there's the network map. And from there, it was like off to the races. So what you can glean from a recon phase is like gold. Okay, so let's call our recon phase over. Like, we're gonna target Max. We're gonna put together some kind of scheme involving this guy and this fraternity. So then what we want is initial access. We think it's a pretty good idea that the data that we want or the system that we want exists within the Neo4j LAN, right? So here's what this looks like. Here's what we know so far. We know that our target is here, that's us, the attacker over there, and Neo4j owns this asset. Well, because of the miracle of firewalls, we don't have immediate logical access to that system, right? So we need to get some kind of initial access into the LAN. Well, what else exists within a LAN is user workstations. And in the vast majority of organizations, the internal network topology is completely flat, meaning that once you're on the network, you can just touch other systems regardless of where else they are or what risk level they present to the organization. I may not have the ability to authenticate to that system, but at least I can ping it, I can hit it on a certain port, I can SSH to it and try to guess a password or something like that. I have logical access to the system if I can get access to that workstation. Making sense so far? So what I'm gonna do, I'm gonna put together this email. And this says, Max, my name is Chris Niles. I'm the Director of Alumni Engagement here at Tau Kappa Epsilon, go Teeks. I have the very distinct honor to let you know that this year, the 8 elected members of the Grand Council have selected you as this year's inductee and the Distinguished Alumni for your achievements in computer science. Wow, great job, Max. But please note, you must complete the attached document no later than end of day Tuesday, October 24th, 2017. Oh my God, that's today. So Max doesn't have time to like vet this guy or call him. Like, he's got to complete this document right now if he wants to be like a distinguished alumni. So as you can probably guess, the document that we're going to have attached to this email is going to be a little malicious. And there are a lot of options as an attacker for what we can do. We could have it be like literally a binary or like an executable. We could have it be like a script, like a bat file or a PS1 or something like that, or a Python script. Or if we want to be a little sneakier and a little more effective and like bypass spam controls and anti-malware controls, we could roll it into some kind of other document that can then execute that script for us. For example, Microsoft Office has tons of ways to run code. You could do it as a macro, you could do it as a DDE, you could do it as an OLE, you could do it as an eval script, like in a cell in Excel. Tons of different options. But the bottom line is, we want Max to run a script for us, and we want him to be encouraged to do it and believe that what he is doing is good for him. So once we do that, what that script is actually going to do is it's going to run on his workstation, and it's going to make an HTTPS connection back to me as the attacker. And this is going to look very similar to just like a web request. And there are tons of different transports I could do. I could do HTTP, I could do ICMP, I could do DNS. You name it, and you can have that as your command and control transport. Now, I have access into the LAN, assuming that Max double clicks on the thing and that the anti-malware doesn't catch it, etc. Believe me when I say that we're pretty good at this. This is actually like the easiest phase of an attack, is getting access to the network. So now we have access. Now, we're in the phase called post-exploitation. Post-exploitation is what separates good pen testers from great red teamers. So anybody can get access to a network. I could probably teach any of you in like an hour how to do this. It's very, very simple. But having the ability to go from like low privilege to very, very high privilege and getting access to your target, that's a little more difficult. That's a little more skill-based, I guess. So 3 vital tools in any red teamer or pen tester's arsenal that you're going to find. First of all, when we land in a network, we don't know anything about it. What we need is situational awareness. We need to know what computers exist, what users exist, what file shares exist, where a user's logged on, etc. Because of the beauty and magic of Active Directory from Microsoft, any authenticated user in Active Directory can figure out almost all of that information. It's actually kind of mind-blowing why Microsoft makes that data available to like very, very low privilege users. I don't know. So PowerView is a solution for this. PowerView is a post-exploitation situational awareness framework by Will Schroeder. It's written in PowerShell. It's PowerShell v2 compliant, which means that if we land on any system that has PowerShell running, we're going to be able to use this. Secondly is a tool called MimicCats. Who's heard of MimicCats? MimicCats is the most miraculous tool that has ever been conceived by man. What MimicCats lets you do is, if you are a local admin on a Windows workstation, and your process integrity is what's called high integrity, if somebody else is logged on to the same system, you can get their password out of memory, you can extract their password out of memory in plain text, no matter how long it is, no matter how complex it is, no matter what the parameters of the password are, you can extract that memory in plain text using MimicCats, which is written by Benjamin Delpy with other contributions by Vincent Letou, two French guys. So the bottom line there is, if I can get local admin rights in a system where an interesting user is logged on, I can get their password, and then I can become that user. And I can continue on in my attack path. And then finally, some kind of agent. So the software that is actually running on the computer that is accepting taskings and then sending the information back to my control server, it's called an agent or an implant or whatever you want to call it. Three good ones: Beacon, Empire, Interpreter. Kind of pick your poison there. Here's MimicCats in action. So highlighted in red down here is a username of a user that was logged onto this system, and then the password there in plain text, password 99bang. Even if there is some kind of like credential guard or other mechanism to prevent credential theft, and even if I can't get the user's password in plain text, I can impersonate the user by token impersonation in Windows, which is a little beyond the scope of what we're talking about, but the bottom line is admin rights equals access to that user who's logged onto the system. So finally, like after I go through that whole escalation process, then I can authenticate to my target, get access to it, and then I'm ready for exfiltration, which basically just means get the juicy data out of the network. Well, the easiest way to do that is just to ride my existing transport back out of the network. So get access to the Neo4j 4.0 source code or the Enterprise Edition license algorithm or whatever, and then shoot that back to my system over my existing transport. Very, very easy. So let's go back a step. I kind of went way, way, way too fast as far as post-exploitation. And that's really what we're here to talk about, is what the problem with post-exploitation actually is. So depending on how mature an organization's security posture is, post-exploitation can be very easy, or it can be incredibly difficult. And at the time, there really wasn't that much in between. So for example, a lot of organizations just give everybody local admin rights, and they have the same password for the local admin user on every workstation. And does that sound familiar to anybody? In that instance, if an attacker gets in and they can become a local admin, that's it, it's over. They're gonna have access to everything. But in a lot of orgs, they're not set up that way. Users don't have local admin rights. The local admin password is different on every system. And so, in that kind of situation, what we have found is that throwing exploits is very risky for two reasons. One, we might knock systems over, which can be bad. As a consultant, that's bad, client management. And then what we can also do is it can trip antivirus, or it can trip other alerts, and it can bring attention to ourselves. Which, if we're trying to be stealthy, we don't want to throw exploits and raise noise or bring attention to ourselves. Secondly, situational awareness is very time-consuming and very tedious. What's funny is that the NSA, before we put out Bloodhound, they had an entire journeyman role that the entire role for that team was just situational awareness. That's all this team of I don't know how many people it was, but that's all they did before we put out Bloodhound. Effective permission calculations for other users is incredibly complex without a graph. Figuring out where I'm an admin is very easy because I just try on all systems, but figuring out for a different user at the time was nearly impossible. And so what we found was there was a very common and very reliable pattern that emerged as we did these pen tests and these red teams and these attacks over and over and over. And these are patterns that you can see in breach reports for Target, Fannie Mae, and other organizations where breach reports have actually been put out. And what this is called is derivative local admin or an identity snowball attack. And here's how it works. Might be a little hard to see this, but what you can see is 4 rows and 4 columns representing computers. And we're going to call this our enterprise LAN. The red computer here, we have access. So we fished a user, we fished Max, whatever, and we have access to one computer. Now, even with our low privilege domain user, we can see where other people are logged on in the network. And so what we can see here is that this user, this DA or this domain admin or this root or God level account in Active Directory is logged on. We know where he is, but we don't have admin rights to his computer. So we got to figure out what to do. So first we're going to do a scan. We're going to scan every computer and we're going to say, tell me if I'm a local admin and also tell me who's logged on to this computer. And then suddenly 3 computers light up and we can see we have admin rights there, there, and there. But none of those users are a domain admin and none of those users have local admin rights in the computer the DA is logged onto. So we have to make an educated guess, like how privileged do we think the user is? Do we think they're going to give us more privileges than the other ones? And this is what we used to do. So we would pivot to this other system. We would get an agent running on that system now. We would use MimicCats, get that user's credential, and then we'd scan the network again. Now we have other computers light up, and we have other users that we have attack opportunity with. But we have to make another guess. We have to just kind of shoot in the dark and figure out along the way what kind of privileges we have. So we'll say we'll go to this computer over here, we'll scan again, and then it turns out we have no further access. So this is just a waste of time going to this computer in the upper right. We have no new privileges. So we'll take a step back, we'll reassess, and then we'll pivot to this machine over here, do another scan of the entire network, and finally now we have access to a computer the DA is logged onto. We pivot over to his computer, steal his password, and now we have access to everything. This is the methodology that we used for years. And so what happened was we were on a red team engagement for 3 weeks. Our execution window was 3 weeks. And it was an organization that did not have only 16 computers in it. It had 250,000. So as you all know, this process doesn't scale. Like doing it manually, it's not going to scale at all. It doesn't. So all the information that we need to figure out where people are logged on, who has local admin rights where, and who belongs to what security groups that then give them more privileges, we had all that information and we were thinking in lists. So we had Excel spreadsheets listing all this stuff out, and we were just tracking all this backwards and forwards, and we were writing Python scripts trying to have this stuff calculated for us, and it was mind-numbing work. It was ridiculous. So I get a coffee with my buddy who actually does have a proper computer science background, and I'm explaining the problem to him, and he puts his water down and he's like, bro, this is graph theory 101 stuff. This is child's play. He explains graph theory to me. I go back, I learn about graph theory, I learn about vertices, edges, Dijkstra's algorithm, A-star, give myself a crash course in graph theory, come up with a proof of concept to automate this workflow, and it worked. So instead of going through this process manually, we could use an attack graph, and we could graph all this stuff out. The result of that was this project called Bloodhound. So the first step with any graph, in my opinion, is the design of the graph. It needs to represent the system effectively, it needs to be efficient, it needs to scale, it needs to be somewhat future-proof. And so the considerations that we have when designing the graph was, first of all, security group delegation. What this means is if I add myself to a group, and that group is a local admin on a computer, I'm a local admin on that computer, and that extends indefinitely. So you can have groups added to groups, added to groups, added to groups, and that group at the tail end, whatever privilege it has, rolls back all the way. Secondly, user credential theft. So the fact that we can get to a computer, we can steal a user credential, and user credential availability, so where users are logged on. We had to take that into consideration as well. And then personally, my goals, I wanted to keep it simple because, like I said, I barely knew what a graph was at the time. And I wanted to keep it flexible enough for future additions to the schema or the design of the graph as well, without having to change the design fundamentally. And so this is the result. It's very simple. The The user here on the very far left can be a member of a group, or it can be an admin to a computer. A group can be a member of a group, or it can be an admin to a computer. And then a computer can have a session for a user. And so a path emerges from the user on the bottom left to the user on the bottom right, along the admin to edge, and then the has session edge. Very, very simple. And so the simplicity of this allowed us to write very simple queries. So here are two examples, and I'll show you what this actually looks like in the interface as well. So effective group memberships for a user is one line effectively. I just do an unbounded search from an origin user to an arbitrary group labeled node. And then for effective local admin rights for a user, I traverse member of and admin to nodes so that I follow those security group delegations all the way until I get to an admin to edge, and I follow those indefinitely. And this is going to work. This is going to work okay because it's very rare for a computer account to be added to a local admins group on a computer. So more often than not, the last edge that this follows is admin to. So very simple, very, very easy. Effective admins for a computer as well, very easy. And then one thing that's very interesting for us is where users that belong to a certain group are logged on. So if there's a group called like SQL admins, and we want access to a SQL server, we want to know where the users for that group are logged on. And so that's what this query achieves, is the group that we designate at the very end here, that my group, follow that back, we see who the effective members of that group are, and then the computers that have sessions for those users. Very simple. To get this data, we have a tool called Charpound. This is written by Rohan Vazarkar. It's based on the original PowerShell collector by Schroeder. It's a C# compiled binary, which you can also run in PowerShell using .NET Reflection, meaning that as an attacker, we can stay completely memory resident, which is interesting for us because most antivirus won't analyze the contents of memory. They'll only analyze what gets written to disk. So if we can stay off disk, we can evade most antivirus, which is great for us. We collect info from domain controllers via LDAP or SMB, and then domain join workstations via SMB as well. The data that we're collecting is local admin group memberships across the enterprise, where users are logged on across the enterprise, and security group memberships. And like I've said a couple times, any user in a domain can collect this information. You don't have to have any kind of existing privilege to collect this. Then the Bloodhound UI. It's built on top of Linkurious, and it's compiled into an Electron app, so it gives us cross-platform ability very simply. We interface with Neo4j using the JavaScript driver from Neo4j. And then we do chunk CSV ingestion through the UI, so we have a bunch of user-friendliness options because we don't want people to have to live in the Neo4j console because they're pen testers and red teamers. They don't care about the graph at all. They just care about the path that they get. So we do CSV ingestion for them through the UI in chunks. And then we also have a modal added so that people can do their own raw Cypher queries and have the interface draw the resulting graph or nodes. So let's check out what the interface actually looks like. So here's the interface. And I have no idea, there it is, there's my mouse. So the default view, when you bring it up, it's going to show you who the members of the domain admins group is. And then as you can see, I can click on nodes, I can zoom in, I can zoom out, I can move things around. This is all thanks to Linkurious, which is built on top of. So as an attacker, there are things that I'm very interested in. I'm interested in effective privileges for other users, for example. So I see a user logged onto a system, I want to know, should I go and try to attack that user? So for example, this random user right here, I can see he doesn't have any local admin rights. This says first degree local admin 0, group delegated 0, derivative 0. These are obviously all running Cypher queries under the hood, and then we present the result, the integer result from the count function to the user here. And then when the user clicks on the number, then it does the query and then it returns a path, and then we draw the path. So we can see like this user belongs to a group here, which belongs to a group here called account operators, which is actually a very interesting group in Active Directory because that group is going to have object control of other objects in AD. So for outbound object control, I'll show you this while we're here. Group delegated object control means that this user, by the groups that it belongs to, what other objects does it have control of in AD? That number is 197, so we can draw that out. And then we can clean this up a little bit by hiding the labels. We can do this, this hierarchical layout, or we can do force-directed layout, depending on like what information is being presented. So, I mean, you can go look at the Licurious booth and like have them show this to you as well. There's also this concept called transitive object control. So transitive object control means this user has control over all these other users here, but these users probably have control over other objects as well. So if I follow an attack path that leads me as far as it possibly can, then we call that transitive object control. And that count here is 475. Which looks a little bit easier in the hierarchical layout, I think. What we also have is arbitrary pathfinding. So I can have a beginning node, just like Google Maps. And I could say, I want to find if there's a path to the domain admins group, which recall is the God account, which of course there is because this user actually belongs to that group. So I can find a more interesting path. If I do shortest paths to here, this just does literally the shortest path query, traversing any edge with no upper bound. So paths of any length from 1 or greater. And you can see the resulting attack paths. So let me show you from here. I can set this as a starting node. I can set this as my ending node. And then I can see the resulting path when I query that out. And as an attacker, this lets me know that if I start as this user, I need to go to this computer, steal this guy's password, and then now I'm a local admin. So this concept for us in our field was revolutionary. I see a lot of like unimpressed faces, which is fine. Like I said, we are not really graph professionals, but this changed our world. This revolutionized things for us. So this revolutionized things to the point that people are actually starting to do attack path automation, which for defenders, for corporate defenders, this is a terrifying concept. There are two main projects. There's one called GoFetch by Tal Mayor and Itai Grady from Microsoft, from the ATA team. And there's also Angry Puppy from Calvin Hedler and Vincent Yu, formerly from MDSec. And then Tal Berry and Tal Mayor, they put out a talk at Black Hat Europe last year, or this year actually, called The Industrial Revolution of Lateral Movement. And basically they were talking about how attack path identification and automation has the potential to completely change the face of cybersecurity. Because before this project was released, attackers would get into a network, and like I showed you that very, very painstaking process, and they would have a lot of opportunities to make themselves known to defenders, and defenders would rely on attackers moving very, very slowly. Now, a process that used to take us 2.5 weeks takes us an hour, thanks to the attack graph. And so now for defenders, there's almost no hope because we can identify the attack path, execute it, have our persistence laid into the network in such a way that the defenders can never root us out. And we can do it in a morning, whereas it used to take weeks or months to accomplish. So for defenders, this is terrifying. Now I've got 6.5 minutes. I'm gonna very, very quickly go through some of this. I'm gonna show you something that I hope you'll find a little more interesting. We added 7 new edges with a dotted release of the project. So we added object control edges. This obviously impacted the performance of the graph because we had all these very highly connected nodes that would have as many edges as there were nodes in the graph. And that multiplied by 7 for whatever graph. And so that increased the size of the database by about 10 times and the number of relationships by 10 times. We have some ideas on how to get around this. And it also exploded the number of attack paths we have available. This is the schema edition for groups. This is it for users. And then using the APOC metagraph procedure, this is what the metagraph looks like. So it got a little bit more complex, but I'm sure for everybody in this room, this is still like probably easily digestible. So we did a talk about Bloodhound 1.3 at DerbyCon. If you want to see more information about that stuff, look at that. I've got 5 minutes and 20 seconds. Bloodhound 1.4, we started adding properties to the nodes. So this enabled us to answer questions like, for every user that has a path to domain admin, who has the oldest password? Or give me an attack path that does not traverse a certain node type or that does traverse a certain node type. Things that you can do with shortest path and the where and with functions. So here's what I want to talk about. So in Active Directory, you have GPO or group policy objects, and you have OUs, you have organizational units. So we are adding very soon into the schema the relationships that let us traverse attack paths that require us to make changes to group policy so that we're executing code on systems or that we're changing user password or whatever. This gets more complicated than what we've done so far. As you saw, the schema is relatively simple. This gets a little bit complex because of the way that GPO enforcement and OU inheritance works. So just looking at the edges and the nodes, you can see that there's a GPO node on the very far left, and it has a GP link edge to this OU. And it has a property on that edge called enforced, which is Boolean, true or false, which means if that edge is true, then the rest of the path, it doesn't matter the properties on any other nodes. That's going to force its way the rest of the path. For OUs, they can have a block inheritance parameter, which can be true or false, Boolean. If the enforced edge is false and the block inheritance property on the OU node is true, then the GPO does not apply to the computer at the very tail end. It gets blocked. This is what it looks like for the whole thing. So you have a GPO on top and a GPO on bottom. GPO on top following the GP link edge is enforced of false. So it's going to get to that top OU. It's going to check block inheritance true or false. It's false, so it keeps going. And then it's going to have two different OUs it can go through. The one on the left does block inheritance, so it's going to get blocked there. It's not going to pass through to the computer on the bottom. And the one on the right, for block inheritance false, it doesn't matter, so it's going to pass to that. The GPO on the middle left, that does have a GP link enforced of true, so the resulting OU block inheritance parameters don't matter. It's just going to follow that the rest of the way. From a GPO to the nodes that it effectively applies to, following this logic of GP link and block inheritance, that's relatively simple. So I can do that with match, optional match, and where from a GPO node to the resulting object nodes. And I can do that in 5 lines. So pretty simple. The other way around, from objects to the GPOs that actually apply to them, is a little more complex. So that looks like this. I'll give you a second to look at that. So this is a little more complex, and I guarantee somebody in this room knows how to write this more efficiently. So that's relatively simple as well. Now, what's difficult is arbitrary pathfinding from an unknown node type to another unknown node type, where I traverse 0 or more GP link edges, and I don't know if I'm going to traverse them or not. So for that, my theory is that we're going to have a custom implementation of Dijkstra's algorithm that is going to store these parameters along the way as it is considering each round of edges that it's traversing. For that, I think APOC is the right solution, and then writing a custom Dijkstra's function for that. I have 80 seconds. So some acknowledgements. Sam Briesmeister was the guy who took me out to coffee and schooled me on graph theory initially. I'm a huge fanboy of Neo4j and graph theory. I think it's incredible, the stuff that you can do with a graph. It's brand new to our industry, to cybersecurity. It's very, very new. There's a lot of opportunity for growth in cybersecurity. Michael Hunger and Max and everybody else in the Neo4j Slack for answering all my really stupid questions. And then the guys at Linkurious, David, Jean, and Sebastian for making Linkurious. This is me. Those are my co-creators. That's our website. And that's my time. Thank you.